So I want to introduce one more lecture around thinking about linear operators for now, and this is really around this concept of Sturm-Liouville theory. So Sturm-Liouville is a really important class of operators that has been extensively used throughout the 19th and 20th century for solving a lot of our canonical problems in physics, including in quantum mechanics, electrodynamics, elasticity, and so forth. And so this is a really important operator, and I want to outline some of the theoretical considerations in its general form so that we can understand some of the special functions that take Sturm-Liouville form, in particular things like Bessel functions, Hermite polynomials, Laguerre, spherical harmonics. There's quite a few throughout literature that are Sturm-Liouville form, have some exceptional properties that allow us to use them in many problems for finding solutions and understanding the physics or the engineering science of it. So Sturm-Liouville theory starts off with this specific form. And this is the most general form, and we're going to talk about the properties of this and what this general form allows us to do in terms of solving problems. So the general problem takes this form here. It's an operator L, and I'll show you what it looks like in a moment, acting on U, and it's equal to mu r of x u plus f of x. So this generalizes the form that we had considered previously, which is Lu equal to f. Now we have this mu, which is a constant, r of x u term over on the right-hand side. And what we'd like to do is find general solutions to this problem here with the following boundary conditions, and these boundary conditions are imposed on a domain. I'm living on a domain from A to B. X is on a range A to B. And so on the left end of the domain A, you have this Robin type boundary condition, which is right here, which is some kind of prescribed relationship between the solution and its derivative. And on the right, the same thing. You have alpha 2, beta 2, which prescribe the value of the function itself and the derivative. And so these are like what are called Robin boundary conditions, and they're very, pretty generic. They're linear boundary conditions, and they show up in quite a few different places where you're imposing structure around the derivative and the solution value itself. So this is the general form of the Sturm-Liouville problem we want to solve. And again, like I said, remember, this is a generalization of what we had before, where we just had f of x on the right-hand side. Now we have this term here. Now the operator L itself takes on a very specific form. The Sturm-Liouville problem is a second-order differential operator, and it takes this form right here. So you see it's a derivative with a minus sign out front, p of x du dx, and then that's all differentiated, plus q of xu. And importantly, what's typically done is there is a set of assumptions or a way that this is typically framed where p of x, q of x, r of x are all positive on the domain A to B. There are sometimes other conventions about whether that minus sign is there or even what the sign of this q of x, whether it's plus or negative. I'm using one of the standard conventions that is used in defining the operator and the functions in that operator for what we want to be doing here. So everything I'll be doing from here on out, we'll be looking at this operator here and the conventions that I have here on this boundary. So remember that associated with this operator are also the boundary conditions that I just showed you in the previous slide. So this is what we want to do, is we want to find a generic way to solve problems that take on this form here. And I've already mentioned this form of operator is really engenders itself well to physics problems. In electrodynamics, oftentimes it takes this form here where the second derivative comes from the wave propagation properties of the electromagnetic field. The q of x is often the index of refraction profile. So you have this structure where you can have waveguides of light, and it's determined by an equation of this form. Same thing with quantum mechanics. The Schrodinger operator, the p of x is 1, so it's a second order derivative, and q of x is typically the potential of the problem. So many of our classic problems that sort of form, in some sense, the the canonical physics training that we get between electrodynamics and quantum mechanics are Sturm-Liouville operators. And so what we want to understand is how eigenvalue, eigenfunction decompositions work in solving these types of problems, because in fact, many problems in physics, that's exactly how you approach them, is through understanding this Sturm-Liouville form. So that's the operator. Keep that in mind. And let's start talking about one other thing that goes with this is we're going to redefine our inner product here. Now, we normally have the inner product, which is just simply the function u and v integrated against each other. But now, I'm going to introduce a new inner product, which is u and v, and this little subscript r. This r denotes the r of x that we introduced in that right-hand side, that mu r of x u. Let me go back to it just to show you. This r of x here, this is a weighting function that's going to play a role in orthogonality. And this is actually very important because there's a lot of special functions that come from physics that really require this weighting function to be there to make sense of the problem. So we're going to define this inner product, and if I have a subscript r, that means when I take the inner product, there's an r of x sitting in there as a weighting between the functions u and v. So it's almost exactly what we had before, but now the addition of this r of x. Without the r of x there, it'll be our standard inner product with the r of x no longer there. So just have this in mind because we're going to be using both inner products in what follows, our standard one and the one with the subscript r. Now, why this is going to be important will be evident in a moment, and it's going to be evident from the point of view of understanding the eigenvalue problem associated with the Sturm-Liouville operator. So this is, in fact, the eigenvalue problem. It's a more generalized version of the eigenvalue problem. And notice what happens here. The r of x shows up in the eigenvalue problem. So it's not just lambda un equals lambda n u of n. I now have this weighting function r of x floating around. And so I've got to account for that. So and this is, in fact, the definition of the eigenvalue problem for the Sturm-Liouville operator. By the way, in many of the applications that we often consider, r of x is typically 1, and so all this weighting factor is irrelevant, and the eigenvalue problem just reduces down to what we're more familiar with. But in general, this is the general form for the Sturm-Liouville, is having that r of x there as a factor. So this is the eigenvalue we'll probably want to consider, and we want to find these eigenfunctions and eigenvalues because with them, we're going to construct a solution to that general form of the Sturm-Liouville problem. So here's the big thing about that r of x. The eigenfunctions of the Sturm-Liouville problem are orthogonal with respect to that weighting r of x. In other words, you have this relationship here, u of n comma u of m in the r norm. So in other words, you have that inner product there with the r of x around there. That's under which these functions are orthonormal. So this is equal to 0. They're orthogonal with the r of x in there. They're all the inner products with respect to each other are 0 except when u of n is equal to when u n is equal to m, and then now the inner product is 1. So so these are orthonormal coordinate system or expansion bases that we're going to use to find solutions with, and it's orthonormal with respect to this weighting function r of x. Like I said, in most cases r of x is 1. However, the more general representation has this r of x not equal to 1. This is something that, by the way, you'll show in some of the exercises that I assigned for homework for this class. Okay, so this is the format. And I want to talk about some of the special properties that happen to hold for these Sturm-Liouville problems. So first of all, the Sturm-Liouville problem is self-adjoint. In other words, L dagger is equal to L, and the boundary conditions for the adjoint problem are the same as for the regular linear operator. So we have the self-adjoint operator, and the self-adjoint operator has some very nice properties. In particular, what we find is a set of eigenvalues that are ordered, lambda 1 bigger than lambda 2, all the way up to infinity. We have an infinite number of solutions, by the way, and you have these associated eigenfunctions with them. And in fact, we can say some very nice things about these eigenvalues and eigenfunctions that we're going to be using to build our solutions out of. So here are the sort of amazing properties that make this Sturm-Liouville problem so nice to work with. So first of all, it's self-adjoint. So the eigenvalues and eigenfunctions are real. So that's a very nice thing. So all the eigenvalues, there's no imaginary component. They're all real. Same thing with the eigenfunctions. You can always write them as real eigenfunctions. The eigenvalues are distinct and ordered. I just showed you the argument before. So there are no degenerate roots. In other words, there's no double roots, triple roots. They're all distinct eigenvalues. And for every eigenvalue, I get an eigenfunction that's orthogonal to all the other eigenfunctions. So a nice property there. The eigenfunctions form a complete set. What this means is I can represent any function in that complete set. So when I think about solving LU equals F, I don't have to worry about solvability because F, I have a complete basis and I can represent any function, any F with it because I have, in fact, a complete set. Okay? So in other words, it spans an infinite dimensional space. And then you have this nice orthogonality, orthonormality property that you get with respect to this weighting function R of x. And remember, when we do eigenfunction expansions, the main thing we do for solving problems, we rely on taking an inner product and using orthogonality. And so we have all these features for us to rely on that are available to us here with this generic form of the Sturm-Liouville problem. All right, so how do we solve the problem? Same way we do any eigenfunction expansion. You simply say, take u of x, expand it in terms of the eigenfunctions u of n, and all you have to do is then find the weighting function c of n. C of n is determined by taking inner product and using orthogonality. So that's what we're going to do. We're going to have to find, first of all, the u of n. Then once we find them, we would then project the f onto those c of n, u of n's to get the c of n's. And I'll show you how to do that right now. So how do we do it? So that's going to be our solution set. So what we're going to do first, before we go to solve the problem, the generic Sturm-Liouville problem we want to solve, let's consider first the following. I'm going to take the function f of x. Remember, I'm solving LU is equal to mu rxu plus f of x. So what I'm going to do is take that f of x and divide by r of x. And I'm going to take this relationship here and do an eigenfunction expansions. It's a complete basis, right? The u of n are a complete basis. So I can do an eigenfunction expansion of just this quotient of these two functions. The only thing I need to determine is the b of n's. So let's go find the b of n's. So the way we're going to find the b of n's is just like we always do. Take the inner product, use orthogonality. So here are the steps. I'm going to take this f of x over r of x, and I'm going to take the inner product with respect to u of m in the R norm. Okay, so this is important. So this is going to be the R norm, and I'm going to take the right-hand side, which is my expansion sum of b of n, u of n, inner product with respect to u of m in the R norm. So first of all, when I take the R norm, let's write out this integral. This integral is from a to b. Since it's the R norm, the R of x is there, and then I have f of x over r of x, u of m. Notice that the r of x cancel. So then what you're really left with here is a to b, f of x, u of m. Now this f of x, u of m, this is just the standard definition of the norm. In other words, this thing here is just going to be f projected against u of m, okay? Without the little subscript r on the norm. Okay, so this is our standard definition of the inner product without the r of x. Now over here, when I do this expansion, notice that this is now the integral r of x, b of n, u of n, u of m. But u of n and u of m are orthogonal with respect to this r of x. So in other words, if I do this inner product, it's always going to be 0 unless n is equal to m, and then it's going to be 1. That's my orthogonality property there. So this whole integral just becomes B of m. So in the end, I find that the B of n, just changing the m's to n's, it's a dummy variable, doesn't matter. So B of n is equal to the inner product of f against u of n. So that makes some sense, right? The B of n are just simply, you take the function f and you project that function f along each of the eigenfunction directions, which are u of n, u of 1, u2, u3, u4, and that's what you have here. And that gives you the weighting along each of the different eigenfunction directions. So what I've done here then is I've decided to take this expansion f of x over r of x and expand this in this form here, b of n, u of n. And I find that the b of n are represented by this. Now the reason I want over r of x is because that r of x is going to be this weighting factor I'm going to carry around. So let's go ahead and solve the problem that we wanted to start with, which was the general Sturm-Liouville formulation. And here it is. Lu is equal to mu rxu plus f of x. So what I'm going to do, well, I'm going to take that u and I'm going to expand it in an eigenfunction expansion. And I'm also going to take that f, and I've already expanded it in an eigenfunction expansion. So everything is going to be expanded with eigenfunctions. So first let's start with the u. So L is acting on u, which is an expansion c of n, u of n's, infinite series. Mu r of x, u, which is, again, infinite series c of n, u of n. And then what I'm going to do now is I'm going to take this thing here. I can take the operator L and move it inside of this sum. So it becomes c of n LUN. But LUN is the eigenvalue problem. That's going to, LUN is going to give me back lambda n r of x u of n. Okay? So there it is. So that just gives me c of n lambda n r of x u of n. Now this here is just a constant. C of n and lambda n are constants, and then I have the r of x u of n. And over here I haven't touched the right-hand side. So everything is now expanded. And now the trick. What's the trick? It's like everything else. You expand, you apply inner products, and use orthogonality. So now what we're going to do is take the inner product of this last expression here with respect to the eigenfunction u of m. And then just take the inner product. So here's how the inner product works. On the left, now I take the inner product with respect to this. I have r of x, u of n, u of m. This looks familiar, right? Because basically, because of orthogonality, this is going to simplify quite a bit. Same thing here. R of x, u of n, u of m. And then over here, because I had that r of x in there already, I just have f u of m. I've already done the expansion. I've already accounted for the fact that I have to take, that I already have the r of x here. And so when I take, I'm just going to multiply by u of m and integrate. The r of x is already sitting here as a weighting factor, both here and here. And this is just straight inner product with respect to u of m. In other words, integral with respect to u of m. And that's why here there is no r of x on the subscript. It's just straight inner product f against u of m. Now these guys here, this is exactly the orthogonality properties we're talking about in terms of this weighted norm. So this here is actually the norm u of n, u of m with the r weighting. Same thing here, and it's 0 everywhere except for when n is equal to m. Okay? So in other words, I'm going to rewrite this r of x, u of n, u of m as this norm right here. U of n, m, the r-weighted norm. Same thing here. And what I know about these r-weighted norms is for the eigenfunctions of the Sturm-Liouville problem, those are 0 or 1. That's it. So when n is not equal to m, it's 0. When n is equal to m, it's 1. And so what you're going to get out of that is all these infinite sums drop down to single values when n is equal to m. And so you have c of m, lambda m, and this gives you mu c of m. And then over there, this is just b of m, which is when we did our expansion of the function f of x over r of x, we did it with respect to b of n, u of m, and that's actually just the representation of the coefficient b of m. And so what you end up doing with this inner product is you get this relationship right here. And this relationship becomes then very important for us, because what we're trying to determine is the C of m. So when do I get solutions? Well, when this holds. Remember, I've computed the B of n, and so now I can pull out, I have this expression here, lambda n minus u, C of n is equal to B of n. And that comes from just rearranging this. Move this to this side over here, and you have exactly this expression right here. So when do I find solutions? All right, so I've got everything reduced down. I'm trying to find the C of n, and there's some different scenarios. Case number one, which is often the case, mu is not equal to an eigenvalue. So suppose this parameter mu here, which was sitting in front of that r of x, u, if it's not an eigenvalue, in other words, mu is not an eigenvalue, lambda n, then it's trivial to solve. You just say C of n is just B of n over lambda n minus mu. Well, that should be a mu, okay? So then we just get a solution. We can get a unique representation for each of the C of n. However, if mu is equal to lambda n, there's two possibilities. One, there are no solutions. So in other words, if mu of n is equal to lambda n, you find that, there are no solutions for this case here. Let's go, in other words, if the B of n is not 0, then you have no solutions. Or you find that mu is equal to lambda n, and B of n is equal to 0, so you haven't violated this, and this is underdetermined, and there's no unique solution. So this is a lot like solving for Ax equal to b. When you solve for Ax equal to b, in most cases what you find, if the matrix is non-singular, you get a unique solution. However, if the matrix is singular, it puts you in a situation where you either have no solutions or an infinite number, and this is exactly the case here. And these two cases here are directly related to the Fredholm alternative theorem. Oftentimes in case 3, what the problem with case 3 is that you actually find that you have a non-trivial null space, and so when you try to find a solution to this problem, you can always add the null space to the solution, and it's still a solution. So you have an infinite number of solutions, and that's the case here. Whereas case 2, it's just singular, and there actually is no solution. Okay? So those are the cases that you have available to you. And again, Fredholm alternative will alert you to these two cases where there's problems. So at the end of the day, with all this calculation, what we find is that the u of x itself is equal to the following. There's your inner product of f u of n. Remember, we're solving for the C of n, which is the B of n divided by lambda n minus mu times the eigenfunction. And this is the generic solution, eigenfunction solution, again provided that lambda n is not equal to mu. So let's do an example of this. So we've computed everything. Everything can be, in other words, everything is just expanded in terms of this eigenfunction basis. And then we just project everything into this space and represent the solution as an infinite sum in this space. So let's do an example. The example is here. U of x plus 2u is equal to minus x. So I have a right-hand side, which is minus x. I have boundary conditions pinned on the left, and this relationship here on the right, which is u of 1 plus ux of 1 is equal to 0. Okay? So I've imposed some kind of more interesting structure on the right-hand boundary condition. So let's first set the problem up. And here is the setup of the problem. I have rewritten it like this. So the Sturm-Liouville form is minus uxx equals to 2u plus q. Now notice what I did here. In this formulation, if in the Sturm-Liouville form that I gave you, I have to have a minus sign in the first derivative, and if I took a minus sign on both sides, it would be minus uxx minus 2u. But the form I had there had to have the q of x being positive, and it would be negative in that case. So I move that to the other side, and that becomes now my r of x is 1 and my mu is equal to 2. So here's the values. The p of x is 1. The q of x is 0, r of x is 1, mu is 2, and f of x is x. So I put it in the standard operator form. So it's really important when you write these down is to fit it into the form that's typically represented as the Sturm-Liouville canonical form, right? And then from there, pick out what the coefficients are. And also respect the fact that Q of x, P of x, Q of x, R of x are all positive. Okay? So this is the form of the solution. And that gives me everything I need. And it tells you that my mu is 2, for instance. And so that's an important piece of information that I have, because mu is part of the solution. Remember, I had the lambda n minus mu on the bottom of my generic solution, which is right here. So mu is 2. I'm going to actually show you that the eigenvalues are never 2, so there's no issue. OK, so first, let's solve the eigenvalue problem then. With those in hand, what we have is the eigenvalue problem is the following. Here it is, minus u of n xx, lambda n u of n. So this is actually a pretty simple eigenvalue problem to solve. Solutions are sines and cosines. And so there's sines and cosines with square root lambda n. And so what we can do is, if you actually solve this, the more details are in the notes. But here it is. I mean, basically what you end up with, if you do a little bit of work on this, here's your normalized eigenfunctions. There they are. They're a sine, square root lambda x. And here's the normalization factor to make sure that the length of this function is 1. And the eigenvalues satisfy this interesting transcendental relationship right here. So in other words, I don't have the eigenvalues in a very simple form. They are the roots of this equation right here. And there's an infinite number of them. Okay, so I have to solve for the eigenvalues coming from this transcendental equation. Once I have them, I can construct these eigenfunctions that, that I'm going to use to do an expansion with. Okay, so the eigenvalues, eigenfunctions can be completely determined, and I have an orthonormal complete basis now to expand my entire solution with. So let's go ahead and take this problem and expand it. So the first thing I need to do, remember, is in the problem, it is a infinite sum of the eigenfunctions divided by lambda n minus mu, and then times the b of n. The b of n is the first thing I'm going to calculate. The b of n is my function f, the forcing, against u of n. Well, the forcing f in this case was just x, and the u of n was this eigenfunction here, which is constructed out of sines. So this is not that hard to integrate. You have an x sine square root lambda nx. You can easily do this, and you find that this integral is, it's not that hard to do. There it is. Okay? Remember, the x only shows up here and here. This here is all just some constant in front. So this is your expansion. This is the b of n. Once you have the b of n, you can construct what the f of x looks like in terms of that basis, and then your solution itself, u of x, is equal to 4, and then I can put the b of n, and over here, look how you have lambda n minus 2, 1 plus cosine, and you can basically work the whole thing out. And notice that there's your eigenfunction, the orthonormal eigenfunction. There's the lambda n minus 2, and you get 1 over the lambda n from here, which comes from that integral there, and it's right there. So this is a complete expression for the solution of that problem in terms of an infinite series expansion of the eigenfunctions that satisfy the boundary conditions and take on the form of that Sturm-Liouville operator. So this is how you would go about solving these problems. I mean, basically, the idea is, if you have a second-order differential operator of the form of the Sturm-Liouville, you have all these wonderful properties that come about. And many of the special functions that we think about that like I said, that I mentioned previously, Legendre, Laguerre, Bessel, Hermite, Chebyshev, all these are Sturm-Liouville form. They have amazing properties around having distinct eigenvalues, an orthonormal set of eigenfunctions that are complete basis. And so we use these often in these physics-type problems because, in fact, in many of these physics problems, what we observe are real functions and real dynamics, and often that's enforced by the structure of a self-adjoint Hermitian operator. So these are the kind of connections we can start making to physics, and this Sturm-Liouville operator is probably one of the most important that we will consider overall. And if you can have an operator that's in Sturm-Liouville form, you're very lucky, because everything falls out nicely from them. So I want to end there. And because I think that now that you know about Sturm-Liouville, we're going to use that in other contexts as well. But what we've seen overall with this eigenfunction expansion technique is a method by which, solving L equals F, we produced essentially the inverse of this function in terms of a sum of these underlying eigenfunctions of the problem. And so that's one technique for going after the inverse of the problem. And then what we're going to present more of is Green's functions, which are a different way to represent those solutions, or that inverse.